Mathematics is one of the finest expressions of the human spirit. It was developed in many different cultures by people observing the world in which they lived, trying to recognize order and coherence in the hope that they could predict and perhaps control future events. Mathematics was born when primitive man felt the need to count, and it evolved as a written language 5,000 years ago when calendar makers calculated the onset of the seasons. Centuries later, the Renaissance scholar Galileo wrote, "The great book of nature lies ever before our eyes, and the true philosophy is written in it. But we cannot read it unless we have first learned the language and the characters in which it is written. It is written in mathematical language, and the characters are triangles, circles, and other geometrical figures." But the earliest mathematical symbols were not triangles and circles. They were scratch marks found on Babylonian clay tablets, used as calendars, or pictographs chiseled in stone on Mayan temples. With the development of commerce, the need for measurement and counting followed the caravans and the ships of the great trade routes. Land measure, from which geometry takes its name, met the requirements of irrigation and tax assessment in ancient Egypt and Mesopotamia. While constructing monuments such as the Great Pyramids that face precisely due north, south, east, and west, Egyptian architects discovered relations between squares, rectangles, and circles. In ancient Alexandria, geometry and trigonometry were used to measure the size of the earth and the distance to the sun and to the moon. Major developments took place when Greek intellectuals, such as Pythagoras and his disciples, treated numbers and geometric figures as pure abstractions. These ancient playthings of the mind laid the foundation for all the technology of modern times. This program will focus on some of the landmarks in the early history of mathematics. Through the magic of computer animation, we'll visit the Pythagorean theorem, the number pi, and other important ideas that led to the invention of calculus in the 17th century AD. And we'll see them brought to life through visual images in beautifully illustrated manuscripts and books. The appearance of Euclid's Elements around 300 BC was a turning point in human history. This remarkable collection of 13 books contained much of the mathematics known at that time. Well presented and skillfully arranged in logical sequence, it was a masterful achievement that influenced scientific thinking for more than 2,000 years. It laid the foundation for the deductive method, showing that human intellect could discover mathematical truths by pure logic. Originally written in Greek on papyrus scrolls, Euclid's Elements was translated into many languages and appeared in countless editions. In the East, the Hindus of the 7th to 12th centuries AD fashioned their own mathematical symbols, including the Hindu-Arabic numerals we use today. In the hands of mathematicians like Omar Khayyam, a new language of calculation took shape. It is now called algebra, a Latinized version of its Arabic name. The Muslim trade routes brought this new language to Europe, where it displaced the clumsy system of Roman numerals and was later wedded to ancient Greek geometry to produce the new analytic geometry of Pierre Fermat and René Descartes. Over the centuries, mathematics has been a mirror of civilization. From primitive scratch marks used to record the seasons, it gradually developed into a new language by those who made fresh discoveries in the 17th century about the motions of the planets. The written form of this language was governed by words and symbols that represent numbers. We'll see how these symbols evolved in many different cultures. Today, numbers are used for identification in all kinds of human activities. We have telephone numbers, license numbers, Social Security numbers, and zip codes. These numbers do not require arithmetic. There's no need to add or multiply zip codes. At another level, we use the counting numbers 1, 2, 3, and so on to list the days of the month on a calendar. These numbers tell us if one day comes before or after another. Arithmetic begins to play a role when we ask how many or how much. The counting numbers, which are taught to children, are called positive integers, written this way. They have also been written in many other ways. Early Babylonians pressed wedges into damp clay tablets. Ancient Egyptians made ink marks on papyrus. These are Chinese characters, and these symbols were used by the Mayans. The ancient Greeks used the alphabet, capital letters in Athens and lowercase letters in Ionia. These are Roman numerals. These are the symbols inherited from the Arabs. These are binary numbers used in computers. And these are barcodes, or modern scratch marks, used in the marketplace to represent numbers and other information as well. After learning to count, young children learn simple arithmetic. The sum or product of positive integers is again a positive integer. Subtraction produces zero and negative integers, numbers not used by the Greeks. In fact, zero and negative numbers came into common use rather late, sometime around 700 AD. Division creates fractions called rational numbers, or ratios of integers. The Greeks wrote them this way. And here's an example of early Egyptian notation. After using numbers for record-keeping for more than 2,000 years, people began to speculate on the nature and properties of the numbers themselves. This curiosity developed into a sort of number mysticism or numerology, out of which grew one of the most profound branches of mathematics. The theory of numbers was born around 600 BC, when Pythagoras and his disciples began studying properties of the integers. They knew that musical tones were related to ratios of integers. For example, this tone at 440 vibrations per second is an octave lower than this one at 880 vibrations per second. They believed that everything in the universe had a secret related to ratios of integers. If they could uncover these secrets, everything would come together in one great harmony, the music of the spheres. To search for these secrets, the Pythagoreans classified integers in various ways. The even numbers, those divisible by 2. Odd numbers, those that are not even. Prime numbers, which are greater than 1 and can't be factored except as the number itself times 1. Euclid proved that there are infinitely many prime numbers. Composite numbers, those greater than 1 that are not prime. The Greeks knew that every composite number is a product of primes. The prime numbers are the building blocks of the mathematical world. The Greeks would have been amazed to learn that one day prime numbers would be useful in cryptography and encoding and decoding messages sent to the outer planets. The Greeks also introduced perfect numbers, those equal to the sum of their smallest divisors. The first two perfect numbers are 6 and 28. The next two are 496 and 8,128. Although Euclid knew how to generate even perfect numbers, only a few were known explicitly. At the beginning of the 21st century, it was not known if any odd number is perfect. By arranging objects such as mosaic tiles into polygonal patterns, the Greeks linked numbers with geometry. This diagram illustrates triangular numbers obtained by arranging objects to form triangular patterns. The square numbers form square patterns. Here are the first 5 pentagonal numbers, and the first 5 hexagonal numbers. Centuries later, Pierre Fermat uncovered one of the deep secrets of number theory. Every positive integer, 30 for example, can be written as the sum of at most 3 triangular numbers, 4 squares, 5 pentagonal numbers, or 6 hexagonal numbers, and so on forever. A more profound link with geometry came from the Pythagorean theorem. In any right triangle, the square of the hypotenuse is equal to the sum of the squares of the legs. In other words, the sum of the areas of the 2 small blue squares is equal to the area of the large square. Here's how the Chinese proved this theorem. Make 4 copies of the original triangle. Put this here for reference. Now slide the triangles around and keep track of the areas of the blue regions. And we see that a squared plus b squared is always equal to c squared. When all 3 sides of a right triangle are integers, they're said to form a Pythagorean triple. Here's one with 3, 4, and 5, and 5, 12, and 13. Another one with 8, 15, and 17, and there are infinitely many more. Pythagorean triples were known long before the time of Pythagoras. This Babylonian clay tablet, written around 1700 BC, contains 15 examples of Pythagorean triples, some of the numbers being quite large. No one knows why the Babylonians were interested in these triples, and as far as we can tell, they did not know the general form of the Pythagorean theorem. The Pythagorean theorem appears in Euclid's Elements in Book 1 as Proposition 47. This Arabic diagram shows Euclid's proof that can be simplified with computer animation. Drop a perpendicular from the right angle to the hypotenuse and extend it to divide the large square into 2 rectangles. Euclid's idea was to show that this square and this rectangle have equal areas, and this square and this rectangle have equal areas. Animation shows why. All parallelograms with the same base and altitude have equal areas. So all these parallelograms have equal areas, as do all these. And that's all there is to it. So we see that the square of the hypotenuse is equal to the sum of the squares of the legs. Still not absolutely convinced? Make a copy of the small square in the middle of the large square. Make cuts along the sides and out to the edges, and rearrange the pieces. All the pieces from the big square fit exactly inside the other 2 squares. The Pythagoreans believed that everything in the universe, including lengths of line segments, is related to ratios of integers. This belief was shaken to its roots when they calculated the diagonal of a unit square. In this isosceles right triangle, each leg has length 1. So, by the Pythagorean theorem, the hypotenuse has length square root of 2. The Pythagoreans were shocked to learn that the square root of 2 is not a ratio of 2 integers, and here's why. If root 2 is such a ratio, then some integer multiple of root 2 is a whole number. Take this isosceles triangle and expand it by integer factors, 2, 3, 4, and so on, until you arrive at the smallest one with integer hypotenuse. Now we'll find a smaller one with the same property, and here's how. Draw this arc. This distance is an integer, and so is this one. Draw this segment perpendicular to the hypotenuse. These 2 angles are equal, so these 2 sides are equal, and these 2 are equal because they are tangents to the circular arc from the same point. So this is an integer, hence so is this. Now we have an isosceles right triangle with integer sides smaller than the smallest one, which is absurd. So, if we assume root 2 is rational, we're led to an inescapable contradiction. Hence, root 2 is not rational, or as we say today, root 2 is irrational. The Pythagoreans tried to keep this discovery secret. According to legend, the first member of their cult, who made it public, was drowned at sea. The Pythagoreans could not accept the square root of 2 as a number, but no one could deny that it was the diagonal of the square. Some of the logical problems created by the discovery of irrational numbers were solved by an ingenious theory of proportions described in Book 5 of Euclid's Elements. 22 centuries later, this book by Hilbert revisited the foundations of geometry and inaugurated an era of abstract mathematics. Hilbert showed that the Pythagorean theorem, which precipitated the ancient conflict between arithmetic and geometry, also played a key role in resolving it. So the Pythagorean theorem for right triangles is an important landmark in the history of mathematics. We turn next to another landmark which has to do with circles. The circumference of any circle is a little more than 3 times its diameter. The ratio of circumference to diameter is the same for all circles. The exact ratio is a fundamental constant of nature denoted by the Greek letter pi. The area of a circular disk is some number times the square of its radius. This factor is another fundamental constant of nature. Surprise! It's the same number pi. To see why this is true, unwrap half the circumference for reference. Divide the disk into an even number of equal slices and rearrange them to form a sort of parallelogram with the same area as the disk. As we take more and more slices, making them thinner and thinner, the parallelogram becomes more and more like a rectangle with base pi r and altitude r, and the area is pi r squared. This profound discovery was made by Archimedes, the greatest mathematician of ancient times. Here's another method. Divide the disk into concentric rings. Unwrap them and pile them up like this. As you take more and more rings, the stack looks more and more like a right triangle, with base 2 pi r and altitude r. Its area, 1/2 the base times altitude, is pi r squared. Because pi is so fundamental, people have tried for centuries to determine its numerical value accurately. The Babylonians used the value 3 1/8, or 3.125. The Egyptian value was slightly different, 256 divided by 81, or 3.16. An approximation to pi also appears in the Bible. The Old Testament describes a circular basin in Solomon's temple, 10 cubits across and 30 cubits around. If the distance around is measured along an inscribed hexagon, you get a ratio equal to 3. The first systematic attempt to estimate pi was made by Archimedes. He obtained approximate values by using regular polygons inside and outside a circle. When we compare the perimeter of this inner hexagon with the circumference of the circle, we find that pi is greater than 3. The inner hexagon can be expanded by the scaling factor of 2/3 the square root of 3 to form this outer hexagon, tangent to the circle. Compare perimeters again, and we find that pi is less than 2 times the square root of 3. Archimedes kept doubling the number of sides until he reached a polygon with 96 sides, and found these upper and lower bounds for pi. The upper bound, 22/7, is still used today as a simple approximation for pi. For centuries, people in many different cultures refined the method of Archimedes by taking larger and larger doublings. The Chinese found a simple fraction, 355 divided by 113. That gives 6 decimals for pi. They held the world's record for more than 1,000 years, until the use of Arabic numerals provided far superior ways of doing arithmetic. For a long time, people wondered if pi was an exact fraction like 22/7. A ratio of 2 integers, called a rational number, always has repeating patterns in its decimal form. For example, in the decimal version of 22/7, the block of 6 digits, 1, 4, 2, 8, 5, 7 is repeated indefinitely. As people calculated more and more decimals for pi, they searched for patterns that repeat over and over, but none were found. Finally, in the 18th century, it was shown that none would ever be found. So, pi is an irrational number. The word trigonometry, from the Greek for triangle measurement, first appeared in this book, written in 1590. But the history of trigonometry can be traced back to ancient astronomy. Because planets were thought to move in circular orbits, early astronomers were interested in chords of circles. The Greek mathematician Hipparchus, the father of trigonometry, wrote 12 books on chords of circles around 150 BC. This work is now lost, but many of the ideas survived in the Almagest, written some 300 years later by Claudius Ptolemy. The Almagest ranks with Euclid's Elements as one of the great masterpieces produced in ancient Alexandria, a magnificent center of Hellenistic culture, a city founded by Alexander the Great after he conquered Egypt in 331 BC. One chapter of the Almagest consists of a table of chords of circles. Today, this would be called a table of sines. In modern trigonometry, sines occur as ratios of sides of right triangles. The sine of angle T is the ratio of the opposite side to the hypotenuse, and the cosine of T is the ratio of the adjacent side to the hypotenuse. Trigonometry uses these ratios to study right triangles. After calculus became part of mathematics, it was found that sines and cosines also play a fundamental role in analyzing oscillating systems. A marble rolling in the bottom of a bowl, a mass oscillating on the end of a spring, water waves, sound waves, radio waves, and the wave theory of light. In fact, everything we see or hear reaches us through wave motion that can be analyzed with sines and cosines. The mathematics of sines and cosines helps us better understand the world in which we live. The ingenious methods of Archimedes gave us the area of a circular disk and the surface area and volume of a sphere and other special figures. Further development of his methods had to wait nearly 18 centuries until algebraic language became part of mathematics. Spurred on by the invention of the printing press around 1438, a slow but revolutionary change in the development of mathematics began in the 15th century. The cumbersome Roman numerals were gradually displaced by Hindu-Arabic characters. A symbol for zero was introduced, and the decimal notation became commonplace. During this same period, brilliant Italian mathematicians found algebraic solutions of cubic and quartic equations. This stimulated a great deal of activity and encouraged acceptance of a new and superior algebraic language. 2 French scholars, Pierre Fermat and René Descartes, made a landmark contribution to mathematics in the 17th century when they introduced coordinate systems and described geometric figures with numbers and algebraic equations. For example, an algebraic equation for a circle comes directly from the Pythagorean theorem for right triangles. Much earlier, around 200 BC, Apollonius wrote an 8-volume treatise on conic sections, curves formed by cutting a cone with a plane. 2 of these curves are the ellipse and the parabola. When these curves are described by algebraic equations, they involve squares of the coordinates, but no higher powers. Parabolas play an important role in physics. If you neglect air resistance, any projectile moves along a parabola if it is propelled forward and upward and allowed to fall under the influence of gravity. When Johannes Kepler analyzed the orbit of planet Mars and developed his laws of planetary motion, he found that all planets move along elliptical paths. Analytic geometry provides a powerful tool for describing planetary motion and other physical problems. In an intellectual marathon, which can be thought of as a relay race toward the calculus, mathematicians competed to find a general method for calculating areas and volumes of curved figures. The Greek idea was to approximate the curved figures with inscribed polygons. Attempting to exhaust the figure bit by bit, they use an increasing number of sides. This ancient Greek approach is called the method of exhaustion. Analytic geometry revived interest in the method of exhaustion and made it possible to analyze area and volume problems with the help of algebraic equations. This gradually developed into a new and powerful discipline now called integral calculus. At the same time, questions about speed, acceleration, and the behavior of changing quantities led to the development of a new branch of mathematics called differential calculus. Both integral and differential calculus were a culmination of ideas from many sources, including Arame, Galileo, Kepler, Descartes, Fermat, Torricelli, and Isaac Barrow, who shared his ideas with Isaac Newton. Building on foundations laid by these pioneers, Isaac Newton and Wilhelm Leibniz finally ended the race for the calculus in a controversial photo finish. Here's one of their key discoveries. Start with any function. Use the integral to calculate the area of the region under its graph. This gives a new function called the area function. Now, calculate the derivative or rate of change of the area function and, lo and behold, the result is the original function. This remarkable link between the integral and derivative evolved into a valuable tool that made calculus the collective language of science and launched a new era in the history of mathematics.